So now that you've seen a little bit about how the Java memory model works, we've talked a bit about some of the concepts of the Java atomics package in general. We talked a little bit about compare and swap, test and set. These are the low-level hardware instructions. Let's talk about how Java atomic operations are implemented, and then I'll also summarize some of the usage considerations. So internally, Java's atomics classes in the Java atomics package, and actually other parts of the Java synchronizers as well, use compare and swap, or so-called CAS operations, extensively. And one of the things that they use is this thing called compare and swap long, which is part of the unsafe class. This is not intended for use by mortals. It's intended by use for people writing Java and the Java class libraries. And this is what it looks like. We'll talk more about what it does. So at a high level, this is what it does in a sort of a pseudocode-like way. Basically, it's going to kind of use the low-level hardware stuff that we talked about before. And so what it'll do is it will go ahead and take the offset here. We'll talk about the offset in a second. It'll take the object that's passed in and kind of turn it into something that can be indexed into. This is obviously pseudocode because you can't do this with Java. This is how it works under the hood. And it'll then go ahead and take the old value and compare it against the expected. And if they match, it'll update the value and the offset from the object with the updated value and then return the old value. So this is basically just a Java-esque way of doing the kinds of things that rely under the hood on the low-level mechanisms that are available with the underlying hardware and operating system. So let's take a look and see how AtomicLong uses that operation, that compare and swap long method, to do its thing. So you can go and take a look at the AtomicLong class. You can go take a look at the AtomicLong source code. So if you go here, this is, I believe, from grep code. You can go and actually see how things work, and I'm going to walk you through some of the more interesting parts of the implementation. So here's the AtomicLong class. And under the hood, it uses Java reflection. And this is really cool. Notice it has a value called long. The value is called value. It's of type long, and it's volatile. All volatile means in this context is that reads and writes to value will skip the processor caches and go directly to memory, both for reading and writing. So there's no caching involved. And we also have this other field in this AtomicLong class called value offset, which, as you can see, is a static final long. And in the static initializer portion of the AtomicLong class, this is kind of like a piece of code that will be run prior to the first instance of the class being defined. So kind of when the classes are loaded into memory, the static initializer region will be run. It goes ahead and it looks up into the AtomicLong class using reflection to find out where the start of the value field is. So you can see this is a string that says value. That corresponds to this field, and that will use Java reflection to figure out what offset from the beginning of an instance of AtomicLong the value field starts at. And it'll probably start at like 4 or something like that. You don't really care what the value is. This piece of code cares what the value is. It stashes it away. And it's the same for every object. Here's the get and add long method. So get and add long is going to take an object. Keep in mind, this is an unsafe class that the AtomicLong is using. So this is a piece of native code. And it's going to go ahead and take an object, which in this case would be an AtomicLong, and it takes an offset, which is this value offset, and it takes a delta. And what it does is it goes through and it gets the current value at that location. So it reads the value, and it reads an int at that location. Actually, that should probably be a long. It reads that thing into V, and then it's going to it'll keep spinning as long as this thing returns false. So what this is trying to do at a high level is it's trying to get the current value at that location, which it does here, and then it's going to add that update to it. So it takes the current value and adds that value to it. This also gives you a sense of why they want to use compare and swap as opposed to test and set. Because test and set always just tries to set it to 1, whereas compare and swap can set it to some arbitrary update value. In this case, it's the delta. We're adding this delta to the current value, and we're atomically doing that. So the offset is relative to the start of object O, and this is the value at that point, at this particular moment. So that's an atomic read. It should be, like I said, it should be a long, not an int, but same basic idea. And what it'll do is it'll automatically add delta to V if V has not changed since we read it. So if between the point where we read the value of V, between this point here and this point here where we call compare and swap, if nothing has changed, if value still has the same value, we atomically update it with delta. However, if something has changed between this point and this point, we don't do anything to it. We just go back and loop again. So that's the power of these atomic operations. They either do it all in one fell swoop or they don't, and they do it in one fell swoop if the value is what we expect. And the reason we want to do that is because we don't want to have this thing change between this point and this point, because there's no lock that's held during that entire critical section. So this is why we spin. So if things go well and there's no contention, or very low contention, we either don't spin more than once, or we don't loop more than once, or actually we don't loop at all, we just do it one time. And if it is low contention, we might loop a time or two. If there's high contention, we're going to sit there and spin and spin and spin. So these atomic operations work best if there's a relatively low contention. If there's high contention, then you're spinning an awful lot. Here's how get and add long is used by atomic long operations like get and increment and get and decrement. So the get and increment operation is basically sort of like, it's like I++, if you're familiar with, it's an atomic version of I++. So you get the current value, which will be returned, and you increment it. There's also one called increment and get, which is kind of like ++I, where you increment the value, and then you return the incremented value. So get and increment is like I++. It's what's called a post increment. And the way it works is we try to add 1 to the current value. Or actually, it's not we try to. It'll just keep spinning until it does that atomically. Get and decrement, look at what get and decrement does. It's pretty clever. It does the same thing, except it adds -1. So it decrements it by 1, right? So this adds by 1, and this decrements by 1. And it should really come as no surprise that, there's also get and sort of add whatever you want. So you can actually add arbitrary values, not just 1. You can increment by more than 1 or decrement by more than 1. There's also methods for all these things called compare and set. And they're basically just a wrapper around the underlying CAS operation, compare and swap long. So compare and set will take an expected value and atomically update it to the updated value, potentially spinning internally to get that thing done. And that's important to remember this method. These are also interesting methods too, but this is a very important method for you to know because you're going to have to use a variant of this for assignment 1B. Under the hood, it does this with the compare and swap long operation for atomic long. So just again as a little hint to you for the assignment, atomic integer and atomic Boolean are implemented very similarly to atomic long. It's just that one works on an integer, one works on a Boolean. And for your spin lock for assignment 1B, you'll be implementing your spin lock using atomic Boolean. Because all you care about is it locked or not? That's all you care about. So it's a Boolean check. And atomic Boolean is really a thin, super thin wrapper around compare and swap. And it uses something almost identical to what we see here. Okay, a couple usage considerations. Be very careful how you use atomic operations. They spin, right? So they're going to sit there and loop. And so it's best used for low contention. If you have things that don't have a lot of contention, spin locks are great. If they're high contention, that may not be the best thing to do. Even if there's a lot of contention, however, some spinning is actually pretty useful on modern multi-core processors, and that's because modern multi-core processors have a lot of overhead for stopping the processor core from running. Putting the processor core to sleep is a very expensive thing to do. And if you want to learn more about that, take a look at this awesome tutorial by my friend Doug Lee, who wrote most of the Java synchronizers and Java concurrency code along the way, and he explains in extensive detail why you don't want to put cores to sleep and all the crazy things that they've had to do in the JVM to keep cores from going to sleep. There's crazy stuff they have to do. If you watch his video, he'll explain all that. The compare and set methods in the various atomic classes provide you a nice portable and higher level means of accessing those low-level operating system and hardware-specific compare and swap operations. So you don't have to program directly to the Java unsafe stuff. Instead, you can use atomic Boolean or atomic long or atomic integer and so on, and be able to access those things at a higher level. So take a look, in particular, atomic Boolean compare and set. That's what you're going to want to get familiar with for your assignment. Okay, so that's the end of this piece.